to announce the talk here of Professor Michael Bronstein. And Professor Bronstein is a professor at Imperial College London and also head of graph learning research at Twitter. And he has a remarkable career and in science and had received a number of awards and recognitions and grants, including 2 ERC grants. And his work is world known, especially in the topic of geometric deep learning, a term that he coined somehow. And this is also where this lecture series is now going about. And it's my great pleasure to give you the stage and listen to your lecture series.
Thank you very much. Thank you for the invitation. So it's always great to be in Cambridge, though virtually, and probably I'm less than 100 kilometers away in London, but still doing this talk through video conference. So I would like to talk. So this is the first of the series of 3 lectures about geometric deep learning. So this is a topic of the book that I'm writing with my co-authors, Joan Bruna, Taco Cohen, and Petra Veličković. And we also gave a course in the summer in the African Master Program in Machine Intelligence. So this is halfway between a course and one talk, so it's a little bit more elaborate. So if you heard Petra speaking before in July, so I apologize, maybe there will be some repetitions. It's based on the same material, but I hope to show some more details. So in essence, what this will be about is some fundamental principles that underlie deep representation learning and most of the modern deep neural network architectures. And if I were to boil it down to just a single word, this will be about symmetry and how it is manifested in different deep representation learning architectures and systems. And if there is one big idea that should be highlighted, I think it's science and engineering, I think it's symmetry. And here I'm quoting Hermann Weyl, who said that symmetry as wide or as narrow as you may define its meaning is one idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. And Weyl himself is credited as one of the creators of the mathematical foundations of modern physics. And in his book that he wrote after his retirement from the Institute for Advanced Study in Princeton, he traced the ideas of symmetry and the special place it occupied in science and art in ancient times, from Sumerian symmetric designs to the Pythagoreans, who believed that the circle was so perfect due to its rotational symmetry. And in fact, the term itself has Greek origins, or symmetria literally translates as same measure, and ancient Greeks used this term to somehow vaguely convey the beauty of proportion in art and harmony and music. And Plato, for example, considered the 5 regular polyhedra, what is today called the Platonic solids, so fundamental that they must be the basic building blocks of nature. And actually, it was not very far from truth, because probably the first one to analyze rigorously from mathematical standpoint the composition of matter was Johannes Kepler, the famous German astronomer. And in his book on the 6-cornered snowflake that he sent as a Christmas gift to his friend, he tried to explain mathematically why water crystals have a 6-fold dihedral structure. And he attributed it to special packing of particles, which anticipated a lot our modern understanding of how matter is formed, and still holds today as the foundation and the basis of modern crystallography. And the methods that were used to describe what are the structure of water crystals or other solids are geometry. And geometry also has its roots in ancient Greece, and the seminal work of Euclid called Elements was what we now call the Euclidean geometry, because that was the only geometry that existed for over 2000 years. And at its core were 5 basic assumptions or postulates upon which this building of geometry was created. And for hundreds of years, the 5th postulate about parallels somehow defied any attempt to prove it. And what happened in the 19th century, that this monopoly of Euclidean geometry came to an end, and there was really a remarkable burst of creativity that made geometry into probably some of the most exciting fields of mathematics. And there are multiple disparate developments, such as the development of projective geometry, which I think is not exactly classified as non-Euclidean one, by Poncelet in the beginning of the 19th century. And then the first work of Nikolai Lobachevsky, who created what is now nowadays called hyperbolic geometry. Even Gauss himself entertained with these ideas, though never published. Janusz Bolyai, and then Gauss's own PhD student, Riemann, they created this remarkable zoo of different geometries that actually put a question on what is actually geometry, how different geometries are related to each other, and how one can come up with a new one and define a geometry. So that created a little bit of an unhealthy situation towards the end of the century, where people worked on different types of geometries and probably even maybe hated each other. So it was not only mathematical, but also to some extent philosophical debate. So the solution to this problem, or at least a new approach, was proposed by Felix Klein. He was only 23 years old when he got an appointment as a full professor at the University of Erlangen in Bavaria. And as it was customary, and probably still customary in German universities, he was asked to deliver an inaugural lecture in conjunction with his appointment. And actually, this is a legend because he indeed delivered such a lecture in 1872, but it was to a layman audience about mathematical education. So what is now known as the Erlangen Programme was the content of a booklet that he published in the same year. And in this booklet, he proposed approaching geometry in a radically new way as a study of invariants or symmetries, or properties that remain unchanged under some class of transformations. And you can easily see that if you take some geometric properties, if you take a shape and you subject it to certain transformations, you will see that certain properties are preserved. So for example, symmetries that define Euclidean geometry are rigid motions, right? So these are translations, reflections, and rotations. And a lot of properties are preserved by rigid motions, such as angles, distances, areas, parallelism of lines and their intersections. But if you go towards a broader class of transformations, such as, for example, affine transformations or perspective transformations, you will see less and less properties preserved. So the language that Klein used in his Erlangen Programme to formalize this notion of symmetry was the language of group theory, which was also a new shiny tool in mathematics that was developed in the 19th century. And the term actually goes back to Galois, who died in his very early years in a duel. And Klein himself, with his colleague Sophus, contributed to the development of some of the basic concepts of this discipline, in particular in geometry. So I should say that, well, Erlangen University, of course, takes pride in the association with Felix Klein, but he stayed there for just, I think, 3 years or so, then moved to other places, eventually settling down in Göttingen, which was probably one of the leading places for mathematics at that time, where Gauss himself had worked. And the circle of his collaborators and students became very much influenced by these ideas, and so the impact of the Erlangen Programme on geometry and mathematics in general was very profound, and it also spilled into other fields, in particular physics. And Amy Noether, who also worked in Göttingen in the same period, for example, was able to prove that every differentiable symmetry of the action of a physical system has a corresponding conservation law. And if you think of it, this is absolutely remarkable result, because conservation laws beforehand in physics were entirely experimental. So you would take a physical system, you will make an experiment thousands of times, you observe, for example, the energy before and after, and you would come up with a conclusion that energy is preserved. So Noether's theorem showed that the conservation of energy emerges from translational symmetry of time. So it's a rather intuitive idea that, for example, if you perform the experiment today or tomorrow, it should be the same. So it was probably the first time that such fundamental things can be derived from first principles. And while that I quoted in the beginning, actually tried to develop these ideas first to derive electromagnetism from first principles and introduce the concept of gauge invariants that first he tried to unsuccessfully unify with gravitation. And then these ideas caught up with the development of quantum mechanics through the notion of what is called gauge invariance, and in slightly more elaborate form. It was generalized by Young and Mills in the 50s, and this created a unified framework that successfully merged all the fundamental forces of nature with the exception of gravity. So this is what is nowadays known as the standard model, and it unifies the description of electromagnetism, weak interactions and strong interactions using the language of these gauge symmetries. So this is all the physics that we know. Again, gravity still doesn't fit. And I think it will not be an exaggeration, and here I'm quoting another Nobel-winning physicist, Philip Anderson, that it's only slightly overstating the case to say that physics is the study of symmetry. So symmetry is fundamental, and at this point, you may ask actually, what does it all have to do with deep learning? So I think there are two connections. So first of all, it is probably without any doubt nowadays that in the past decade, deep learning has created a true revolution in data science, and some tasks that were maybe impossible or even at the level of science fiction 10 or 20 years ago now have become feasible, whether it's computer vision, speech recognition, natural language translation, playing intelligent games such as Go, or more recently even protein folding. At the same time, we have now a situation that reminds a lot what happened in geometry in the 19th century. We have a zoo of different neural network architectures for different kinds of data, but very few unifying principles. And as a consequence, it's difficult to understand the relations between different methods. And as a result, there is a lot of reinvention and rebranding of the same concepts in this field. So what we try to do, and this is what geometric deep learning is about, is some kind of geometric unification in the spirit of the Erlangen Programme. And I don't want to sound arrogant here, so we're obviously not comparing ourselves to the great Klein, but just using the same mental picture and the same mindset of his Erlangen Programme. And there is really dual purpose to it. So first of all, we can call it pedagogical purpose to provide common set of mathematical tools or a framework to derive some of the most successful and popular neural network architectures from first principles. So not to teach deep learning as a set of hacks and empirical ideas, but more as a principled framework of which some of the popular architectures are particular settings. And this is what I will try to convey in these lectures. And also, second, you can ask what will happen beyond deep learning in the next decade, for example. So in a sense, you can think of it as a constructive procedure to incorporate prior knowledge into neural networks or maybe future machine learning systems and build such architectures in a principled way. So the term itself, probably I can take the credit for coining it for my ERC grant in 2015, and then we popularized it in a paper that appeared in the IEEE Signal Processing magazine. And nowadays, geometric deep learning is often used synonymously with graph neural networks, even though I hope to show you that it is way broader ideas. And as I mentioned, we are writing a book with Joan, Taco, and Petar. And earlier this year, we published a proto version of this book in the form of a long review article. So you're more than welcome to see some of this material on the website geometricdeeplearning.com. So let us have a look at machine learning. Maybe it's in its naive or simplistic setting. In the setting of supervised learning, it is essentially a function estimation problem. So we are given some unknown function, like, for example, if we want to tell apart cats and dogs, we have a function that inputs an image and produces a binary label. And we can observe this function and its outputs on the training set. And we try to find a function that fits well with training data and allows to predict the outputs of inputs that we have never previously seen before. And again, image classification is a classical example from problems in the domain of computer vision. And what happened over the last decade or so is that two trends essentially coincided. So first is the availability of large high quality data sets such as ImageNet, which has millions of labeled images. And on the other hand, the growth of computational power, in particular GPUs, special hardware that initially was developed for graphics applications, but somehow luckily it coincided with many architectures such as convolutional neural networks in terms of the structure of the data, what is called SIMD, single instruction multiple data architectures. And these trends together have led to the possibility to design rich functional classes that have the capacity, at least in principle, to interpolate such large data sets. And neural networks appear to be really a suitable choice to represent functions because even though we know neural networks for many years, and what I show here is a very simple architecture from the 50s, the perceptron. If we connect such simple neural network to at least 2 layers, so we get a one hidden layer architecture, it produces a dense class of functions, or in other words, we can approximate any continuous accuracy to any continuous function to any desired accuracy. This property is called a universal approximation. And the setting of this problem, if we consider it in low dimensions, is really classical problem in approximation theory, where we have a lot of results and error bounds, for example, telling us how many samples we need to produce in order to obtain a certain error. So this has been studied very extensively over the past century or so. But as it happens, the situation is entirely different in high dimension. And unfortunately, machine learning problems are high dimensional. And here as an example, we can see that if we take even very well-behaved functions, such as Lipschitz continuous functions, and the example shown here, this is from probably often given, and we take it from the book that we are writing. So here we have a superposition of Gaussian blobs that are put in the quadrant of a unit square, and each blob can come with a plus or minus sign. So you can easily see that in order to incur certain approximation error, you need to take the number of samples in the quadrant of this unit square. And as the dimension of this, well, in this case, it becomes hypercube, grows, then the number of samples will grow with the dimensionality. So it will become order of d, or 1 over epsilon to the power d. So we get a phenomenon that is called the curse of dimensionality. And even with very modestly dimensional inputs, the number of samples that we will need to take will be more larger than the number of particles in the universe. So it is absolutely infeasible and intractable problem. And there are, well, some additional results that followed on this topic of universal approximation theorem. So we can see that the curse of dimensionality still exists for other types of regularity. For example, if you consider Sobolev classes of functions, or Baran was, for example, able to show that for a special class of functions, it is possible to avoid the curse of dimensionality, but these assumptions are probably too strong to be valid in practice. So if we look at this problem of curse of dimensionality, one of the classical examples where it's manifested and where the early problems emerged is in image analysis and computer vision, like classification of images shown here. So even very tiny images are very high dimensional, right? So if we consider the MNIST data set, it's about 32 by 32 pixel images, which are approximately 1,000 dimensional. So they're extremely high dimensional. And if we were to apply a perceptron on this image, we need somehow to vectorize it, to break it into one-dimensional vector. And this can be done, for example, by stacking the columns of the image and feeding it into the neural network. And you see that this way we throw away a lot of structure, right? So if I shift the digit by just 1 pixel, I will get a very different input. So I will need to tell the neural network in the form of data augmentation that all these shifted positions are the same digit and should be classified in the same way. So data augmentation, maybe not in this silly and naive form, is a very common technique that is used nowadays in deep learning. And I hope to show that there are better alternatives in some cases. So in computer vision, maybe again, just historically, the remedy for this problem came from classical works in neuroscience, where it was shown that the connectivity of the visual cortex of the brain is organized into what is called local receptive fields. And this served as an inspiration to a new class of neural architectures which share local weights. So the first instance of these architectures was neocognitron of Fukushima, which in many senses anticipated the modern deep learning. So for example, it used half rectifiers, which is almost considered the ReLU activation function, considered almost one of the hallmarks of modern deep learning. It was already there in 1980. And of course, the classical work of Jan LeCun and co-authors on convolutional neural networks, where the concept of weight sharing across the image effectively solves the curse of dimensionality, and also incorporated some forms of invariants, about which we'll talk during these lectures. So let me show you another example, and this takes us already to a different mindset that goes beyond this nicely grid structured data. So what you see here is a molecule represented as a graph. So the nodes here are different atoms, and the edges represent chemical bonds. So if you're curious, this is the molecule of caffeine. So you're probably very familiar with this molecule from everyday life. And it's a very common problem in chemistry, such as drug development and drug discovery, to be able to predict some properties. So for example, I would like to predict how well this molecule can be dissolved in water, or whether it is toxic, or whether it binds to its protein target, right? What would make a good drug that achieves what it should do and doesn't harm the patient. So in this case, we can still take the same approach as we did with images. We can take the nodes of this graph, order them in some way, and feed them into a neural network. The problem is now that the ordering is really arbitrary. We don't have a canonical ordering of nodes of the graph. And in images, at least we had some lexicographic order, right? We could do column or row stacking. So there was some way of canonically ordering the nodes of the grid. In this case, we usually don't. So you can already see that the geometric structure of the underlying object is very different. And this will lead us to concepts of permutation invariant. Molecules are just one example of this kind of irregular non-Euclidean structured data on which we would like to apply deep learning techniques. And there are many prominent examples, probably some of also from our everyday life, are social networks. So when we use Twitter or Facebook, we are actually a node in a giant graph that has hundreds of millions of nodes, multiple billions of edges that connect different users and explain and model their relations and interactions. Also, our body, we can describe it as an interaction network of different molecules, metabolites, and so on. And this is what is called interactons that are very popular now in biological sciences, also in problems of drug design and repositioning. If we go to computer graphics, we can model three-dimensional objects as meshes, which are simplicial complexes or graphs with some additional structure, and so on and so forth. So let us go back to this problem where that was cursed by the curse of dimensionality, the multi-dimensional image classification problem, and let's see what we can do here. So fortunately, it's not just a d-dimensional vector. We have additional structure that comes from the geometry of the input signal, and we call such structures geometric priors. And as I will show in these lectures, it is a general powerful principle that allows to address otherwise dimensionality cursed problems in a principled way. So specifically in this example of image classification, the input that before we considered as a d-dimensional vector is not a d-dimensional vector. It's a signal that is defined on some domain that I will denote by omega. In this case, it's a two-dimensional grid. And I will denote the space of signals on the domain by x of omega. Okay, so what we'll be doing, and this will be the recurrent pattern in this blueprint of geometric deep learning, we will be modeling the structure of the domain by a symmetry group, G. So this is, in case of images, for example, the group of two-dimensional translations that act on the points on the domain omega. So we can take a point and translate it by an element of the group. Now, in the space of signals, the actions of the group on the underlying domain are manifested through what is called the group representation, denoted by ρ. So to make this example more concrete, in our case, the image is represented as a d-dimensional vector, and ρ will be a matrix of size d by d that acts on this d-dimensional vector. So in this specific example, it's the shift operator. Okay, we'll talk about it when we'll be talking about grids. So this the next step is we are applying a function that acts on these images. So it takes as input the images. So we have this hierarchy of geometric structures. So we have a domain omega, which is described by the symmetry group. We have signals defined on this domain, which are described by the group representation that acts on them, right? Like images in our example. And then we have functions that are defined on these signals. And the structure of the group will be manifested in the design of the function through notions of invariants and equivariants. So one particular class of functions that are unaffected by the action of the group are called invariant functions. And a good example is image classification. That was actually one of the rationales for the design of convolutional networks, if you look back in history. So if we consider an image classification example, I have an object in the image, I don't care where the object is located, right? So if the cat is moved around the image, I still want to say that this is a cat, right? So this is an example of shift invariance. On the other hand, we might have cases where the structure of the input and the output is the same or related. And a good example is image segmentation, where we try to label each pixel in the image. So the output will be a pixel-wise label mask. And what we want in this case is that the output to be transformed in the same way as the input, or what we call a group equivariant function. And in this case, it's an example of shift equivariance. So somehow, ideally, if we want to classify digits or symbols, what we want to do, we can imagine a neural network that has multiple layers, and one layer, for example, allows to distinguish between all the possible geometric transformations of our digits or our letters. Like in this case, all the instances of the letter A will be identified to the same representation. And then, for example, we have another layer that is able to identify all the different styles of the letter A. The problem with this approach and why we never have invariant representations in intermediate layers of neural networks is that to analyze complex scenes, we need to consider them as a collection of parts. And the relative positions of parts seem to be important. So here I'm citing Hinton, but it was probably observed way before, in even not in computer vision, but in Gestalt psychology literature. So you can look at the image as a collection of parts, and I can rotate the entire image, or can rotate its individual parts. So if my intermediate representation that looks at these parts is rotation invariant, I will not be able to tell, for example, between the situation in the middle and the situation on the right. So we lose this way critical information. And that's why the typical architecture that we see in image analysis, and this will also be the general blueprint of geometric deep learning, is a sequence of equivariant layers that produce equivariant representations that are possibly followed by some aggregation layer, what is called pooling, that is invariant to the action of the group. So we keep equivariant representations in the middle, and then we aggregate them into an invariant representation. So in convolutional networks, the equivariant layers are convolutional layers, and the invariant readout is a fully connected layer. And it's important to emphasize that the convolutional layers are really equivariant translations, and you can see it if you take an input image and you apply to it a convolutional kernel, you see that the output is transformed in exactly the same way as the input. You can apply the same ideas to other types of transformations like rotation here, and well, it's a little bit hard to see what happens here. So we have an input that is rotated, and the output of a convolutional layer It also rotates, but you can also see that it changes. So just to make it easier to visually study, let's stabilize the view, and you can see that there is no translation equivariance, right? So the feature map is not only rotated, but also changes. So it is possible to generalize convolutional neural networks to make them equivariant to more general group transformations. And here is an example of rotation equivariant CNN. And you can see that in this case, in the stabilized view, there is no motion whatsoever. And I should say that the structure of the domain and the assumption of the group that we make on this domain are completely separate things. So even in the plane or on two-dimensional grid, we might have different types of transformations. So it is typical to assume translations, but we can also have, for example, translations and rotations, or we can also have reflections. So all these can be incorporated as this inductive bias as a structure in our architecture. And I think there is no really a common recipe because it depends on the application. So you can imagine a situation when you have a self-driving car that wants to recognize traffic signs. So in this case, I think it's reasonable to assume, because all the traffic signs are more or less are put in a certain way, and the car doesn't tilt. It is only translational invariance that you're interested in, right? But if, for example, we have a flying car, right, an airplane that you can imagine on the highway, well, maybe a little bit made up situation, then of course rotations are also important. But reflections are not physical unless you see a traffic sign in your mirror, right? But if, for example, you take another kind of application, if you look at histopathological samples, so you have a thin slice of tissue, biological tissue that you need to put under a microscope, their reflections are very natural because you can put it, you can flip the glass, and you don't have a canonical orientation, right? So it can be both translations, reflections, and rotations. So there are many problems where you know a priori what is the right structure, and what you gain in this way by making your architecture account for the right geometric transformations is that you will typically require much less data, and also you will have certain guarantees about what kind of representations your architecture produces. So this is a way of considering equivariance as symmetry consistent generalization. So in this case, you can imagine that you have two images, right? So let's call them x and x prime. So these are, let's say, two styles of the letter A, and they can undergo different geometric transformations, let's say rotation. So we can model it again as an application of some group representation that I denote here by rho 1, the representation of the input space. So here we have rotated versions of the letters. And let's say that we are building a neural network that creates some representation of the input such that we can identify the two styles of the letter A, right? So what cannot happen is this situation. So if we have an equivariant architecture, this cannot happen because equivariance will guarantee that the rotation, right, or its representation commutes with the function itself. So the features of of these two letters, if they are transformed or not, will be the same, related by the transformation. It's important to emphasize here that because the structure, even dimension of the input and the output space might not necessarily be the same, we might need different representations for the same group. So that's why I denote them by rho 1 and rho 2. Now, as with any model, this is a little bit of an idealized picture. So it's a little bit of wishful thinking to assume that you can describe your transformations by a group, right? A good example is a video. Here are two frames. One car moves left, another one moves right. So there is no really a global translation. So you cannot explain the relation between these two frames by a translation group. Or probably you can do it only locally. So a more appropriate model here will be a model of automorphism, so some deformation of the domain. So a map that I denote here by tau that maps from the domain to itself. So you can think of it as a kind of warping of my image, right? So I can compose it with the image, and I denote the representation of this warping as a linear operator L with subscript tau. So you can also think of it as a group, right? If you consider bijections, so it is closed under function compositions. So it is a group, but it's a very large group, right? So we are actually not interested because it can completely permute all the pixels in the image. So it doesn't preserve any structure, right? Besides the very coarse set properties of this domain. So we want something more interesting, right? And here we can consider the translations as a subgroup of this very large and very broad and very too large group of automorphisms and bijections. And as we've seen before, for example, translations can be considered as elements of this group. But if we have something that looks a little bit like translation, right? So here you can see that this image is not only shifted, but slightly distorted. So I see that this tau somehow will be sufficiently close to my group, right? So I can try to quantify it. So I need some extra construction. I need either a norm or a metric that will tell me how far my deformation is from being a pure translation. And we call these properties geometric stability. So you can measure the kind of deformation and sensitivity, or more broadly, you can generalize the notions of exact invariance and equivariance in this form of an upper bound. So in case of, for example, these smooth deformations, it was shown by Joan Bruna and Stéphane Mallat that you can bound using the Dirichlet energy, right, the norm of the gradient of this deformation field, the difference between the output of this function f applied to the original signal and to the deformed one. And this is a form of stability under deformation, and they used this analysis to explain why convolutional neural networks are so successful. So they are not only have exact translation equivariance, but they are also stable under approximate translations. So this is a generalization, of course, of shift invariance, because if you have a pure translation and the Dirichlet energy is zero, and in this case, we get back the standard shift invariance. So here I should probably make an important difference between what we call signal versus domain deformation. So what you see on the left is an example where you have a fixed domain, for example, a graph, and we have some signal changes. So imagine that you have the spread of infection, which is a very actual and relevant topic with this pandemic. So the domain is it has a fixed structure, and what changes are the attributes of the nodes. So what you see on the right is a different situation when we have a graph that changes. So in a social network, for example, a new user can come, or users can leave the network, can create or terminate social links. So this graph will be changing. And in applications in computer graphics, where we have manifolds that model three-dimensional objects, for example, deformable shapes like our own human body, are actually examples of a domain that deforms. So again, this is the situation of a signal that changes on a fixed domain, like what was shown on the left is some form of diffusion on the manifold, and on the right, the domain itself deforms. So if in the previous case, we're interested in a signal that is defined on some domain, like our grid, and for example, we could say that if we have a group that acts on the domain, we have a group representation that acts on the signal, and we want a function that is invariant under this group action. And in this case, we are asking the question, what happens if now we deform the domain? So we have another domain, omega wave, that is a deformation of the domain omega. And for example, we can say that if we have a function that is intrinsic and we're interested in isometric deformations, then such functions will be invariant under isometries. And of course, this can be generalized to the more broad case, right, where we have something that is approximately a group. And as in the case of Dirichlet energy, we can measure how far this deformation of a signal is from the group. So in case of deformation of the domains, we can tell how far two domains are from being an isometry of each other. So when we talk about deep learning on manifolds, I will go slightly in more details about these concepts. So another important geometric prior is what is called scale separation. And in multiple cases, it is possible to construct a multi-scale hierarchy of domains. For example, in case of grids, this is typically done by coarsening. And in case of graphs, we can also coarsen the graph in certain ways. And this coarsening assimilates nearby points on the domain. So again, we need some extra notion of typically a metric. And it produces a hierarchy of signal spaces that are related by what is often called the coarse graining operation. So I denote the new domain, the coarser domain, by omega wave, and the space of signals respectively. So in this space of coarser signals, we can apply another function that we denote by f wave. And then we can ask what are the relations between these signals and these functions. And we will say that the function is locally stable if we can approximate it as the composition of the coarse graining operator and the coarse scale function. So you can think of, for example, image classification. If I can downsample my image and then apply a classifier at the coarse scale, and it will work as well as in the regional scale, then our function is locally stable. And what happens is that while the original function f might depend on long-range interactions on the domain, if the function is locally stable, we can separate the interaction across scale. And this is often done, often used in image recognition. For example, in convolutional networks, this is typically implemented in the form of pooling. And actually, this principle is very general, and it is often employed in physics. So, for example, fast multiple methods exactly use scale separation to approximate interactions at long range and assimilate particles that are nearby. And you can see that together, these principles give us a very general blueprint of geometric deep learning that you can recognize probably in the majority of popular deep neural architectures. So we have a sequence of equivariant layers that act on domain with a fixed structure. And also, in many cases, we can show that these equivariant layers are also approximately equivariant, so they're geometrically stable. We can have a global readout layer that produces invariant pooling. And then we can also have some local pooling. In this case, we need some mechanism to create a hierarchy of domains and coarsen the signal on these domains. So again, this is typically the local pooling that is done in convolutional networks and in other neural network architectures, such as graph neural networks and so on. And this is a very general design. We can apply it to different types of geometric structures. So grids are obvious. We can also apply them to more general homogeneous spaces where the groups act transitively and we have a global symmetry structure. We can apply them to graphs and to manifolds. So this is what we call the 5G of geometric deep learning. So on manifolds, as I will show, we are interested in two types of invariants. Invariants under the global deformation, so this domain deformation stability, as well as the choice of the local frame. So this is what is called gauge invariance, and it's exactly the same concept that is used in physics. And what I will try to show you in these lectures is that the implementation of these principles in the form of inductive biases can lead to some of the most popular deep learning architectures that exist nowadays, whether it's, for example, convolutional networks that you can derive from considerations of translational symmetry, whether it's graph neural networks or deep sets or transformers that can be derived from permutation invariants, and intrinsic and mesh CNNs that are used in graphics and vision that can be derived from these concepts of gauge symmetry. There are also recurrent networks and LSTMs that can also be described in the form of time warping, but I will not talk about it. So you can see that basically it's a kind of a plug and play approach. So you can choose your domain, choose your symmetry group, and you will get the popular architectures, but the underlying principles remain the same. So that's why it is a little bit similar to Klein's Erlangen program, where he could plug in a different symmetry group and get a different geometry. So that's why this a little bit arrogant analogy is probably close to what we are trying to achieve here. So in the next lectures, I will focus on the particular instances of this blueprint of these architectures. So we'll be talking about graphs, grids, homogeneous spaces, and manifolds. And then in the last lecture, we'll be talking about applications in some open research directions. So I will probably stop here. I don't want to start the next topic, which will be graphs, and we'll be glad to answer any questions. Thank you very much.
Yeah, many thanks, Professor Bronstein, for your excellent, instructive lecture. So do we have any questions?
I have a question, but yeah, maybe, I don't know, maybe this is not a smart question, but I was wondering, or very intuitive, very, yeah, I mean, very, it's something that everyone understands. Okay, on this domain, you need translation. In this domain, you might want something that we understand well. What about be relevant, where you might even learn the certain group?
Yeah. So, well, the audio was not great, but I understood the question is about how to detect symmetry from the data. So I think this is a question that I am asked very often. So it's about time that I probably form an opinion. So I think short answer is there are some works that try to do it. It's not straightforward, especially because well, we try to avoid the cross-dimensionality in this way, but still we somehow need to assume that the symmetry group is tractable, and if it's a finite group, then we need that the number of elements is small, right? So, for example, permutations are intractable; they have n factorial of elements. If it's a continuous group, then the dimension, right, the number of parameters should be small. We cannot write integrals, right, computer integrals over a 10-dimensional space. So there are some works that try to detect symmetry. So in a sense, in graph neural networks, you can think of transformer or self-attention architectures as this kind of architecture where you assume that the graph is complete or fully connected, and you essentially learn the right structure from the data. So it's a little bit a far cry from truly discovering the symmetry. So there are also recently lines of works on equivariant message passing. So it's a combination of different structures. So you do message passing on a graph, but you assume that the graph itself has geometric features, and molecules are really the motivation for it, because it's not just a graph. So you're not only interested in the topology, but it's also geometric structure. So it is embedded in R3. And that's why, for example, you want to account for different transformations, rotations, and translations of the molecule. Yeah. So the short answer is there are multiple works, but it's still an open question, and you can also see why. So if you imagine images where imagine that you have images that are mostly translated horizontally in one dimension, but you have also a little bit of translation up and down, right? So what is the right description? Is it a one-dimensional group, and then the other vertical translations are absorbed into some error, right, some deformation, or you describe it as a two-parameter group of horizontal and vertical two-dimensional translations, right? So there is no quick answer, right? So it's kind of trade-off.
Thank you. Great. Thanks.
Many thanks. Do we have another question? I wanted to ask, if there's no question, I wanted to ask one question. Can one also, I mean, say, are there some thoughts also about, given the specific form of the data and then the architecture of the network designed as these instances of geometric deep learning, are there also some thoughts about the training procedure, like by means of gradient descent methods that take these thoughts into account, or are there any thoughts in this direction?
Yeah, it's a good question. So I think, well, at least maybe this is still wishful thinking, but probably these ideas are invariant to the way that you train. And well, nowadays machine learning is primarily implemented by backpropagation. So you solve some optimization problem by gradient descent. So that's how it is implemented now in the form of neural networks. But you can, in principle, think of other implementations of learning that work differently. So it is not. It is in a sense orthogonal to these principles. So of course you can do if you have, for example, I don't know, let's say if you have rotational symmetries, right? So this is a manifold, right? So it's a Lie group. So you can use optimization techniques that actually incorporate this differential structure and take it into account. So you will do something like Riemannian optimization, where you do steps in the tangent space of the manifold, and then you project back to the manifold. So you constrain your variables to lie on the manifold. And this is quite popular topic, I think, nowadays in optimization, manifold optimization. So it is also used maybe a little bit exotically in deep learning, but probably more so. And I think you can find it, for example, with graph neural networks, where you consider graphs embedded in non-Euclidean spaces, in hyperbolic spaces, for example. So there you must use this form of optimization.
Mm-hmm. Many thanks. Are there any other further questions from the audience? So if this is not the case, then let's thank Michael Bronstein once more for his excellent lecture. And yeah, we look very much forward to continue tomorrow.
Thank you very much.
Just wanted to add a nice lecture, and I'm looking forward to tomorrow.
Thank you.
Okay, bye-bye.
Thank you. Have a good day.